SwayamPrabha. Digital India. Educated India.
Welcome back. In lecture 29, we will look into water treatment, and this is the second part. So, the concepts that would be covered in this lecture are on aeration, plain sedimentation, and then coagulation, flocculation and clarification. So, aeration is the process which promotes exchange of gases between the water and the atmosphere. And usually we add oxygen to water, and when we add oxygen to water, it increases the freshness, and usually it is effective for sources which are from underground and these are deficient in oxygen. So, because it is not in contact with atmosphere, so usually there is less amount of oxygen in this kind of water. So, addition of oxygen will improve freshness of that particular water. Then we also add we exchange this, the exchange of gases also involves removal of dissolved gases, which causes taste and also results in some odor, and this is again effective for water from deep layers of reservoir, which usually have got dissolved gases such as carbon dioxide and hydrogen sulfide. And sometimes aeration can also precipitate impurities such as iron and manganese by formation of certain oxides and all. So, concentration of gases in liquid follow Henry's law, which says that the concentration of gas is proportional to the partial pressure above the liquid. Now, what does partial pressure means? Product of volume of percent of gas and the total pressure of the atmosphere. So, this is the principle that is used in the process of aeration. So, the rate of exchange of gas depends on many factors, and these are utilized to design different sort of aeration or aerators for the water treatment process. So, these properties are actually used for that. What are these properties? The area of interface between gas and liquid. So, more the area, more would be the exchange. Smaller the droplets, more is the surface area. So, if we make the water droplets smaller, so we can actually increase the surface area, that increases the area of interface between gas and liquid. Or if the water is applied in a film, that means as a layer, and usually it is applied over a packing material or sort of a filter media, some some particles or some either it could be like certain kind of activated carbon or coke, or it could be something even like a brick bats and all these things. So, all this packing material, the smaller the packing material is, more is the surface area for that particular film, and that will actually increase the exchange as well. Then thickness of the interlayers, that is agitation of surface, increases also the exchange. Then time of contact, by how we can increase the time of contact? By increasing the height of the jet or droplet. So, if I spray the water into the at a higher height, obviously it will take more time to fall down. So, it has got more time for coming in contact with air, and that means time of contact could be increased. Or in case of packed media or this packed material that I was talking about, if its height is raised, that means the water passes down through those media and it actually has got more time in contact with that. So, that actually also increases the time of contact. The partial pressure of the gas, that is air injected into a main under pressure. So, the more is the pressure, then more would be this exchange. And then degree of undersaturation or oversaturation of the gas, that means existing percentage of gas in the liquid, that also determines the rate of this aeration. So, as you can see, that means product, that is percentage volume of gas as well as the total pressure, both are playing a role in determining the exchange of gas that happens. So, the basic process is aeration, and it is achieved through formation of drops or films of water exposed to ambient air, and it is achieved in different kinds of aerators. The first kind is basically a spray aerator. So, as it is evident from the term itself, the water is sprayed in form of mist or droplets, and there are trays and fixed inclined nozzles. The trays actually collect the water when it comes down, and these inclined nozzles are actually results are used for actually spraying the water. So, this actually helps in removal of gas to 70 to 90% of CO2 and 90 to 99% of H2S. So, probably we will go using this kind of aerators when there is lot of H2S mixed in that particular water. So, we have to decide based on what is the constituent of these gases in the water. Then there is waterfall or multiple tray aerators. So, this is basically we have a spray, it is collected in a tray, but here we have got multiple layers. Over in this picture you can see that the raw water is inlet over here, it is raised up, then it falls down these different trays. So, this is the first tray, this is the second tray, this is the third tray, and as you can see there is coke, which is basically the filter media. So, the water passes over that, and that actually results in removal of the water coming in contact with air and removal of this particular gases. So, eventually it comes down and then it gathers in this basin, from there it will be taken out. So, we have got a riser pipe which raises the water, and it is distributed to a series of trays or steps. Water falls through the edges or bottom to a collection tray at the bottom. Coarse media is used, coke, stones, stone ceramic balls, these are the different things that we can use. Removal of gas 90% of CO2 and 60 to 70% of H2S. So, see over here CO2 could be almost removed from this particular water. Then we have got cascade aerators. Water flows over an inclined surface downward, and turbulence is ensured by passing water through baffles or steps. So, because it is a cascade, that means if we have a cascade like that, so automatically when the water falls down there is lot of turbulence over here, and that actually results in mixing of water with air. So, either this could be steps like that, or we can have baffles of different sizes. So, that means the water jumps over that. So, that also actually results in this cascade flow. So, removal of gas over here is very 20 to 45% of CO2 and 35% of H2S. So, its effectiveness is less, but it is, as you can see, it is very easy to construct, as evident from this particular image, where we show a cascade aerator at Hiriyatka water treatment plant in Manipal. Right. So, this is how the water is being actually coming down from the top. Then finally, we have got diffusion aerators, that is where we use the process of aeration through forming of small bubbles of air which rise in water. That means, we use pressured air inside the water, and that forms bubbles which raises through the water, and that actually helps in mixing of water with air. So, we have a basin with perforated pipes or porous tubes, then compressed air is used to pass through these perforated pipes. This result in formation of bubbles, and the tanks are 3 to 4.5 meter deep and 3 to 9 meter wide. So, this gives you an idea about the size of those units, right. So, depending on how much one aerator can take, you have to determine the flow rates, and you have to determine the number of this kind of units. And this kind of units take lesser space than spray aerators, and this is higher initial and operating cost. So, these are the different kind of aerators that we use. Next, from aeration we go to plain sedimentation, and plain sedimentation is the process of removing heavy sediment load from raw water prior to coagulation, and particles heavier than water settle under gravity, whereas finely divided solid and colloids remain suspended. And as we have learnt already, that means for those kind of colloids and all, we use coagulants which is mixed into the water, and that results in we can actually mix it through flocculation, and then this form coagulants, and this gradually sediment as well as due to sedimentation they will come down, and clarifiers could be used to remove those sediments, right. So, sedimentation is involved, the basic process of sedimentation is used both in plain sedimentation as well as coagulation with sedimentation. In both cases we use this process. So, usually when we have, that means in plain sedimentation we usually have discrete particles, and we also are aware of their settling velocity, that means at what speed they will settle, and then we have got flocculent particles as well. So, this is when we mix coagulants. So, discrete particles they do not change shape, size or weight during settling. So, when they are settling, their size, shape, everything remains same, they just come down. Discrete particle settles at uniform velocity because it is not changing any shape, weight or anything. So, usually the velocity of settling or coming down is more or less same. That velocity is very important. I will explain why it is important, because that will determine the time for which you have to keep the water inside that particular tank. So, you have to give that time for these particles to actually settle down, right. So, the time you retain water in a sedimentation tank depends on its settling velocity. So, acceleration, so this is determined based on acceleration due to gravity, because it is falling down due to gravitational forces, and the frictional resistance of that particular liquid. So, it is a combination of both that results in the settling velocity. Whereas, in case of flocculent particles, agglomerates forming clusters of different shape, size and weight, and this actually keep on increasing even though when it is falling down, and that's they settle faster due to increased weight. So, it is a little bit, the speed is different from the in case of plain sedimentation. So, what influences the factors influences the process of sedimentation? So, of course, the size, shape and density of that particular particles, viscosity, density and temperature of water, because it offers the frictional resistance, surface overflow rate, that means at what rate you are water is flowing into that particular chamber, velocity of flow, inlet and outlet arrangement, the detention period, how long we are going to detain that water, and effective depth of the settling zone. That means how much is the depth of that particular tank. All these things determine the process of plain sedimentation or the process of sedimentation. So, any kind of settling tank design or sedimentation tank design will have inlets, a settling zone, and then we also have got outlets as well, and then there is also a zone for settling down and all. So, we will discuss that. So, we have inlet which ensures incoming water is uniformly distributed across the entire width of the tank. So, as you can see, these are the common type of inlets. So, once water comes in, this side is the tank, this side is the tank. So, the water is actually taken down and it's sent via like this, or in this particular case the water is taken down and then there is a baffle, and from here the water actually mixes. Over here the water is coming over here, then it moves to the next level, and then over here it again moves like this. So, these are the different designs of inlet. We are not, we do not need to be too, we are not going to design inlets for sedimentation tank, of course, but at least you know that we first need to ensure that the water is spread out into the entire tank. Then the next part is the settling zone, in a continuous flow settling tank, that means there is a tank, water continuously is coming in and it is continuously going out. So, that means we design the volume of the tank based on the time for which we want to detain that particular water. So, if I want to detain a particular water for 2 hours, that means whatever water comes within the 2 hour period, this should be the capacity of the tank. So, in continuous flow settling tank, both horizontal and vertical movement of particles happen. So, that means water is coming from here, it goes out from this side. So, definitely the particle is moving in a horizontal direction, as well as because of gravity it goes down like this. So, as you can see over here. So, on one side is the horizontal velocity and then there is the settling velocity on this side, right. So, this is the resultant velocity resulting out of the movement of particle that happens because of both these velocities, right. So, this is how the particles falls. So, particles follow a parabolic path and enters the sludge zone, which is this is the sludge zone. So, we have to also estimate the size of the sludge zone in a particular tank, and time required should be less than the detention time. So, that means the time for the particle to start from here and then come down, this should be less than the detention time, that is the time required to move from one end to another for this particle. or that means from entry to exit, whatever time is there, it should be less than that. So, detention period is basically the capacity of the tank divided by rate of flow. We just discussed that. So, usually for mechanically clean tank, where the sludge is removed mechanically after certain intervals, then it takes 2 to 4 hours. For normal tanks where it is not mechanically cleaned, it is for 4 to 8 hours. So, that is how we design the size of this particular tanks. So, detention period and the rate of flow will determine the size of this particular tank. And flow of water per unit surface area is basically the surface loading, that is how much water we need to load per square meter of the surface. So, you usually have surface loading rates for this kind of tanks, and because they are spread all over the surface, that then only it starts falling down. So, surface loading is also important, and then for that we can also follow this relationship where L by small v is should be greater than equal to H by small Vs. So, what is L? L is length of settling zone, H is depth of water in settling zone. So, length, this is the length and this is the depth, and V is the horizontal velocity of flow of water and Vs is the settling velocity of particles. So, L by V should be greater than H by Vs. So, that we should ensure that one. So, there are also formulas to determine settling velocity and all. So, I am not going into that much details. So, let us look at the settling tank design. So, we have the sludge zone in addition to the settling zone, we have the sludge zone below that, as I was telling you, and this ensures that all settled particles are conveniently removed without disturbing the settling zone. So, we have to give adequate space for that, so that it does not disturb the settling process. And why disturbance is the issue? Because we give a sort of inclined surface at the bottom, and the sludge gradually moves downwards, and sometimes we have mechanical means for scraping the sludge, as we can have systems like this, which with rotating arms, which actually rotates and then make sure that the sludge goes towards the center. And then over here we have a mud valve. This is a sort of gate valve which could be operated by electricity, as I was mentioning earlier. This opens up at certain intervals, and because it's a pressure drain, it's a pressure conduit, we can suck in the sludge from over here, and so that's the mechanical cleaning of sludge. So, bottom is usually sloped in one side or center, and we make sure that all this movement happens in the sludge zone and it does not affect the settling part at the top. So, that is why we ensure all settled particles are conveniently removed without disturbing the settling zone. Sludge is removed via cast iron pipes with gate valve under hydrostatic pressure. So, some amount of pressure, that is how we create the pressure. And then we have our outlet zone water, that means the water that is treated at the top, we take it from via outlet, which is without disturbing again the settling zone. So, these are some of the designs of the outlet. So, this is the wall. So, this is how the excess water comes over the wall and falls into this outlet pipe and then goes out. So, over here you can see that water, this is again another sort of inlet, it goes up, and then from here we can take it down, and then this is the outlet pipe. Then this is again outlet channel inside this particular chamber where the water moves up and then falls down, and then from here we can take it. So, these are the different kinds of outlet that could be designed as well. So, then there are other kinds of tanks as well, like for example, whenever there are different kinds of tanks. So, these are the different zones in a tank, and then we have different designs of the tank. So, we have horizontal flow tanks where direction of flow is mostly horizontal, and within horizontal flow tanks there are different types of tanks. One is radial flow circular tank with central feed. So, in this kind of tank, as you can see and see over here, this is where the influent goes in, this is centrally the influent is going in, and from here the influent goes out, and this moves on this direction, and as it moves then settling happens, sedimentation happens, right. And then this is the mechanical arm, which is like there is a motor over here which moves it, and this mechanical arm goes round and round, it scrapes the sludge that falls settles over here and send it towards the center where we have the sludge sump, and from here it is taken out, right. And the water gradually, it is a horizontal flow tank where the water gradually moves over here and then over this weir then the water goes into this outlet channel, and from here it is taken out. So, this is a circular sedimentation tank. So, water enters at the center of the tank and flows outward radially, uniform radial flow, decreasing horizontal velocity, sludge is scraped mechanically using 2 or 4 arms, both effluent and sludge removed continuously. So, this is the basic design of a circular or a radial flow circular tank with central feed. Then we have also radial flow circular tank with peripheral feed. So, this is centrally we are putting the effluent. Sometimes the influent comes from the outside, from the periphery as well. So, this is how the influent is coming, and we can take the effluent from the center. So, over here we can have a system designed where the clean water comes in and then we can take it out. Or it could be also at the outside, that means influent and effluent both goes from the periphery, but these two outlets are divided in such a way so that the influent comes in, it goes below, then it goes up, and then it goes into this channel, from there it is taken up. So, it is a peripheral feed circular sedimentation tank with effluent and influent channels separated by a skirt. So, that is how we are able to make sure that both this does not mix, and this movement of the water actually results in the sedimentation process, and again the rest is same. We have a scraper over here, this gradually is continuously rotated, and that leads to movement of the sludge to over here to the sludge sump, from where it is taken out via pipes. Then we have got rectangular tanks with longitudinal flow. So, these were circular tanks, but we can also have rectangular tanks, and let us see the first, there are different designs of course. So, first of all, we have got in this particular image, you can see that this is a rectangular sedimentation tank with baffle walls. So, the water comes in, then there are baffle walls, it moves like this, and then it goes. So, these are baffle walls. So, we are continuously making it go like this. So, it flows like this, then it goes onwards, and then eventually it comes out from this outlet zone. So, there are several baffles which are created, and that actually makes the water flow in a particular order. This results in the detention time of the water is determined by the speed of the water through these baffles and all, and this results in, during this entire process, continuously sedimentation happens. So, rectangular tanks with longitudinal flow. So, usually what we do is, if we have a longish, we have a rectangular tank, sedimentation tank, and as you can see in this one, the flows, this is the influent from, this is where the water comes in, and then the water goes into the tank, it flows like this in this direction, longitudinal flow in one direction, and then over here it actually flows into this particular effluent weeds, and then these are channels where, when we raise it after a certain height, then only the water can flow into that, and then eventually it goes out through this effluent line over here. So, during this flow sedimentation happens like this, and below you can see a mechanical scraper, which is a sort of a belt. You can see the same system over here as well. So, this is sort of a belt drive. So, this actually keeps on scraping the sediments which falls over here and bringing it to the sludge hopper or the sludge pit, you can say, from where the sludge is removed. So, there is also this motor actually drives this belt which continuously moves, and in the process it will scrape, that it has got fins like that which will scrape the surface and bring the sludge over here. So, in the first design, the sludge was taken back to the point where from the influent side the sludge actually is put over there. One benefit of this is heavier particles do not need to travel like that immediately when the water is put, the influent comes in, because some of the very heavier particles immediately settle and they come to this particular sludge pit. But the other design is the water goes from enters over here, and then the water enters over here, and then actually the same design just from opposite side. So, only the two mechanical systems are different over here. So, and we also give a sort of floor slope which is approximately 1%. So, more or less in both the system we are putting the sludge collected at the same side as the influent, but sometimes it could be in the opposite direction as well, depends on the design, but usually it is over here and mechanically scraped just to summarize, sometimes this tank operation is stopped for removal of sludge. So, that means we do not do the removal of sludge parallelly with the movement of water. Sometimes mechanically it is scraped to sludge pit at influent end and removed continuously or periodically without stopping tank operations. So, that is also is possible. So, in addition to this longitudinal flow tanks, we also have vertical flow tanks. That means, what happens over here is the inlet is over here, the influent comes in, then it is taken to the bottom and then it is allowed to move upwards, and from there we have got several layers through which we can take the clean water out through the outlet. But in this particular process, we actually, because it is the water has to raise up, the velocity falls down and the sedimentation increases, and that results in collection of sludge at the bottom over here, from where the sludge could be also drawn out. So, vertical flow tanks, it is a combination of sedimentation and flocculation and also flocculation can also happen. So, square, it could be square or circular in shape. They may have a hopper bottom, this kind of shape is, this is called a hopper bottom. Influent enters at the bottom, flocculation takes place, velocity reduces with rising of influent. Flock have to rise through layer of flock, resulting in clarification, because the flock formation happens, and this because flocculation is happening, some amount of flock is there, and this actually when it raises, this is a problem. This actually prevents further have to raise a layer of flock, resulting more clarification happens because it has to push through that existing layer of flock. So, clarified water is withdrawn from the circumferential or the central weir. So, from here from either from the circumferential weir or from a central weir, we can remove this particular water. So, it could, that means the outlet could be also at the center. It depends on design, how you design this particular system. So, this is the image of a longitudinal flow tank, and this is the mechanical scraping this unit that you can see over here. And then usually rectangular tank design, this is the most common design. Usually the length is around 30 meter, but sometimes it is something also around 100 meter. So, that will give you an idea about the size of this kind of sedimentation tanks. The length to width is 3:1 or 5:1. So, this is the ratio, and usually the tank is kept narrow to prevent cross currents and eddies, because that will affect the sedimentation process. We have to reduce the amount of current, and longitudinal baffles in the long tank to continue confined flow in straight channels. So, usually to make sure that the water goes in the longitudinal way, then we give this longitudinal baffles as well. So, these are the basic designs of a plain sedimentation tank, and here you can see the different the loading rates and the detention periods. Based on this, you can determine the size of the tank. For plain sedimentation tank, then for horizontal flow or circular tanks, then vertical flow or upflow clarifiers. So, this is where we can use this kind of sedimentation tanks in case of flocculation, because as you will see that flow, it helps in flocculation part, this vertical flow tanks, right. So, both this kind of tanks could be used both for plain sedimentation as well as for even after coagulation. We can use if we have separate units for flocculation, coagulation, then we can also have separate sedimentation tanks as well. But anyway, in most cases this is for plain sedimentation. So, the surface loading rate is how much amount of influent or water we can apply based on the surface area of the tank. So, for plain sedimentation, typical values are 15 to 30, but we can have very big sedimentation tanks as well. So, 15 to 30 meter cube per meter square per day. Then horizontal flow 30 to 40 meter cube. Then vertical flow or upflow clarifiers around 40 to 50 meter cube per meter square per day. And the detention period is again typical values are 3 to 4 hours, and then 2 to 2.5 hours for horizontal flows or circular tanks, and vertical flow tanks 1 to 1.5 hours. So, this is the detention period, and based on that and based on the depth of those tanks, you can determine the size that is required for this kind of tanks. So, usually in plain sedimentation we remove sand, silt and clay. In horizontal flow and circular, this kind of tanks we can use it after after using coagulants and clarification happens. So, that is alum and iron flock could be removed, and flocculant could be removed in vertical flow clarifiers. So, these two kinds of tanks could be used after even the use of coagulants. Next, we discuss the process of coagulation, flocculation and clarification. So, already the sedimentation part is, you can see that the sedimentation units are already discussed beforehand. So, usually we see that very fine particles such as suspended clay particles cannot be removed by plain sedimentation, and even for silt, which is a relatively larger particles, silts are of different sizes. If the size of silt is around 0.6 mm, we have seen that it requires 10 hours to settle in a plain sedimentation tank, 3 meter deep. So, you can understand the time. That means, you have to design a tank which will hold the water for 10 hours. So, that is a big amount of detention time, that will require a huge size of tank. Similarly, for silt of 0.2 mm, it will require 4 days. So, we cannot have storage for 4 days, because that will, there is no point of having such a large tank in for water treatment. So, instead we have to look into other ways to actually get rid of this kind of particles. So, that is why fine and colloidal matter is removed through coagulation, where what we do is we mix certain chemicals with the water, which forms an insoluble gelatinous flocculant precipitation, and this also removes color, odor and taste from water to certain extent. And this entire process, as we have discussed, it involves coagulation, flocculation, clarification, sedimentation and sludge removal, followed by filtration. That means, eventually this has to be followed by the process of filtration, right. So, usually it is not left after just clarification, but we have to also do filtration. And parallel to clarification, we also have sludge removal. So, the sludge is also removed and dealt with separately. So, the chemical used most commonly is alum. There are other chemicals as well. So, Al2SO4 whole thrice and 18H2O, that is water is also there, and the dosage is something around 0.03 to 13 grams per liter, depending on turbidity. So, you can also determine the size of these tanks where we will store this kind of chemical. So, if you know the dosage per liter of water, then you can also understand the amount of these chemicals used. And in case of very clear water, then the dosage has to be adjusted, it has to be reduced. So, in that case we go for around 5 milligram per liter or 25 milligram to 25 milligram per liter. So, it is roughly this is 30 grams per liter to 130 grams per liter. So, for clear water we use much less. So, alum can be also recovered from sludge, and this could be used at 1/4 of cost. So, if you want to save some money, we can also do some alum recovery, but for that we have to again design separate units. So, alternatives to alum, this is we can also go for sodium aluminate, ferric chloride, ferric sulfate. This also helps in the process of this coagulation, and the dosage depends on, of course, if it's the water is relatively clear or is it turbid, based on that. So, it also depends on kind of coagulant, turbidity we already mentioned, it depends on the color of water, it depends on the pH of water, it depends on the temperature of water, and also depends on the mixing and flocculation time. So, all this will determine what kind of dosage that we will give to this particular for this treatment. So, the process of coagulation, flocculation and clarification, it starts with the process of feeding, that is where coagulants are mixed in liquid and dry form. So, coagulants could be either in the liquid form or in the dry form, but usually when it is dry, there is chances that it will clog or it will form cakes or these chunks or deliquents. And these are the different issues that happen. So, this is what we have to be careful about. And dry feeding is possible with alum, it does not create this kind of issues, and we usually use a conical hopper with revolving helical screws or toothed wheel at the bottom of the hopper to release the chemicals. So, basically hopper is something like this, and then we have this release valves and all through which we can release the chemicals. Then mixing devices are used to mix coagulants with water and rapidly mixed for 1 minute and then gently agitated for 30 minutes to start coagulation process. So, as you can see, it is both rapid and gentle mixing, both is taken together, and velocity of flow of water in mixing basin is something around 15 to 30 centimeter per second. So, this is the velocity of water. So, this is a baffle type basin. So, you can see over here raw water is coming here, and then this is where the chemical feed is actually saved stored. So, this is that chemical storage tank, this is where we can actually mix it, and this is this hopper that we are talking about, it gradually mixed with water, and then the water is coming at a particular rate. So, then we have got a baffle. There could be different sort of mixes. This is a flash mixture. I will show you details of that. That means usually there is a fan involved and it rapidly mixes the chemical with the water, and then gently we allow the water to pass through these baffle walls, and that results in slow mixing. So, this is called a baffle mixer. And then we have got this clarifiers where actually the flock settles or the coagulants comes down, and then via sedimentation, and it settles, and then it could be removed but through sludge. The sludge is collected over here from where the sludge could be removed, and then the clear water goes into the rapid gravity filter and so on. So, baffled, this is sort of a baffle type basin, whereas we have got flash mixture where we have a fan operated by electric motor, as you can see over here, and also there could be a deflector plate mixture where water is agitated by the deflector plate. So, water enters over here, it comes down, then it goes up. So, there is this deflector plate which continuously moves up and down, and that results in mixing with the chemicals, and this is the chemical pipe, chemical is released over here. So, this is where the water is mixed, and then the mixed water goes into the next chamber, and over here the chemical is released over here, there is a fan, it allows in mixing of water with the chemical. Then comes the process of flocculation. So, where we have there are different kinds of mix, like the first part is the mixing of the chemical, but flocculation is continuous mixing of the or continuous agitating that liquid as well as the chemical or to form further coagulants, right. So, it helps in further process of coagulation. So, flocculators provide contact between the flocculating particles, increases the flock formation because more particles come and join together, and it has got multiple compartments, and then there are rotating paddles. So, these are motors which actually helps in rotating these paddles, which keeps on churning the water, which helps in further mixing. And over here the detention time is 30 to 60 minutes. And in this particular chamber you can see the slope of the flow is around 1:150. So, some slope is given, and the inlet is from bottom and the outlet is from the top. So, clarification is the final process where flock is allowed to settle, and clarifiers are fitted with a moving or raking arm which removes sludge continuously, and we usually have we can also have combined units where we have got both feeding, mixing, flocculation, clarification all together, and these are known as clariflocculators. So, over in this particular unit you can see this is the inlet, this is the chemical feed, this is the flash mixer which mixes the chemical, then it goes into the next part where these are rotating paddles, these are horizontal valves, and this could be said vertical rotating paddles, and this actually helps in mixing the chemicals, and then the water goes over here, sedimentation happens, and this is the clarifier which actually helps in removing the sludge. So, this overall unit is called a clariflocculator, or we can also have separate units for each of these processes as well. So, this coagulation, clariflocculators are of different design. So, over here you can see another design clariflocculator. This is a clariflocculator which is totally it's a oval, it's a round in shape, and as you can see in this particular design there is a bridge at the top, and this bridge actually rotates. This is fitted at the center, and sometimes the flocculation zone is at the center. What it means is the inlet, this is the inlet pipe, the water comes in through here, and this is this chamber you can see over here. So, within this and the bridges are fitted with this paddles which actually helps in mixing of this helps in the process of flocculation. That means, it mixes that chemical or formation of this flock formation happens, and then it goes into the next layer where it gradually settles, sedimentation happens, and this is the clarifier which scrapes from the bottom, and then from here the sludge could be collected from the bottom, and then it is taken out, and the clean water goes into the peripheral channel, where through this particular chamber the effluent through this particular outlet we can take out the cleaner water. So, clarifloculators could be of different sizes, 4 meters to 70 meters. Of course, 4 meters is too small, but 70 meters is more likely. Concentric circular compartments. So, the inner zone is the flocculator zone, the outer zone is the clarifier or sedimentation zone, and then we have got the sludge hopper fitted below. Then inlet pipe is in the center. The paddles are also located over here, and we have this bridge which is used both for observation as well as it fits that over here all this paddles are fitted, and the flocculation chamber is inner, this concentric circular compartments, clarifier is at the outer part. The bridge cum walkway, one end on traction carriage and the other end on the bridge center support. So, one is at the center support, the other is on the at the side. It's a traction carriage, you can say, and this bridge center support is a hinge pin over a center mechanism or a turntable. So, this is loose fitted and it helps to rotate. So, it's fitted on a turntable mechanism, right? And flocculators around 2 to 4 are suspended from the main bridge, like over here you can see 2, but there could be 4 as well, and this actually helps in mixing. And there could be again center driven clariflocculators, like the bridge is rotated by a motor from the center, or it could be end driven clariflocculators, or it is rotated from the side as well. So, this is the basic design of a clariflocculator. So, like the previous one, this is another design. So, this is very common design, this you can find in many of our water treatment plants. So, finally, to conclude on this processes, the choice of technology for different operation depends on flow rate, area availability, cost and treatment level desired. So, based on that you have to decide on what kind of unit or what kind of technology you are going to use for a particular process. So, these are the references you can study. Thank you.